So hopefully you'll now see sort of a combination of this presentation as well as this live feed through my webcam here. And you see that checkerboard, you see the sound brush, and I'm going to create a new project and start from scratch and kind of show you this procedure. So I'm going to say create. I've got the sound brush hooked up to the laptop, obviously. I'm going to create a new database. These are all the existing databases that I have on my computer. I can open these up and look at the results anytime I want. In this case, I want to test a new object, so I'm going to create a new project. And it's going to essentially talk to the sound brush, and it sees automatically that I have the intensity transducer plugged in and instead of the 1/2-inch mic, so it knows I'm going to be measuring intensity. I set my unit system. In this case, I have my dimensions of my object known are in inches, and so I'm going to work in the English system. I'll call this white noise. Got a little noise maker from my daughter's room that we're going to do some very important testing on today. And then I can pick whether I want to test in the 3rd octave spectrum or in the narrowband spectrum. In this case, I'm going to select the narrowband just because narrowband actually gets me both narrowband and 1/3 octave. I can specify my frequency resolution, and essentially this is going to limit or extend how fast I can move the sound brush. If with a coarser frequency resolution, I need a shorter time to take that data so I can move the brush faster. I want a little bit finer frequency resolution, about 11 hertz, so every 1/10 of a second or so, I'm taking a data point. The sound brush software is going to track how quickly I'm moving the brush, and it's going to tell me if I'm moving too fast. We don't want to smear our location during a measurement. And then I can specify what kind of windowing I want to use. As we're producing real-time time to frequency information, we need to window that to reduce our leakage. And then we have this average mode, which allows me to decide how I want to handle data measured at the same position. Let's say I've passed through the same XYZ coordinate multiple times. Do I want to keep the last value? Do I want to linearly average all 5 data points, let's say, or do I want to just peak hold? In this case, I'm just worried about peak hold in this instance, but maybe averaging is more appropriate for what you want to do. There is my project. I'm all set up. Next, I'm going to go to this Setup 3D. And this is where I could load a 3D model. So if I have an STL file or something from my object or my front of dash or whatever it is, I can just load an STL file. In this case, I'm not going to use a 3D model just because I'm going to do a real simple basic test. So I'm essentially just going to resize this cube that it makes for me and just make it roughly the right size and shape. It's never going to be circular like my actual object, but I can make it essentially the same size. It is 5 inches in diameter, and it's 3.5 inches tall. So you see my object got quite a bit smaller. This bigger area here is this measurement area. So if you imagine a cube that's this size on each side, that's the volume inside which I'll be able to collect data. Intensity vectors will populate in any XYZ position within that cube. I don't need to know information maybe this far away from this object, so I can make this a little bit smaller, and let's say I'll just make it a foot or so. So it'll be the dimensions of my object plus a foot in every direction. But as I'm testing, if I move the sound brush outside of this area, it's going to tell me you're outside the measurement area. I'm not going to take data out there. And so this allows me to just sort of only take data where I want to take it and not take more data than I really want. And so you see I've got a 3-dimensional rough representation of my noise machine here. And then we also see this sort of little origin floating around. And this origin, its location is at these defaults right here. And what this has to do with is that stand and that checkerboard that you see over here. The reference is at this position right here, at the top right corner of that bottom left square. That is where in 3D space, in reality, this origin right here needs to be positioned. And so by default, if I move all of this stuff for you here, so you see that's my test object. And essentially those defaults, if I were to, let me take this board off of here for a second. If I were to place this stand up against the front edge of my object, and then if I were to bias it all the way over here to the left side of my object, so that, let's see if I can get a better view, so that this edge and the bottom of my stand are aligned. Got a tough viewing angle here, but then that reference point is automatically properly located, okay? Because I have a small table here, I'm not able to put the reference in that default location. But you see the reference board gets held by that stand, and so that's how it knows the default location of this point right here. So all I have to do is in the software, and let's see if I can move this over. So I can adjust these default values to essentially localize that origin in the right spot. And so what is a little bit off is I have to slide this origin along the negative red axis. So I've done some calculations, and essentially I want to move it to the left. Okay, so now you see the origin should be, you know, sort of off the left edge of my noise maker here. And if I remove my board again, you see that the edge of my stand is indeed about 4.5 or 5 inches to the left of the left edge of my noise machine. This is maybe a little bit too much detail, but essentially, if you are smart about where you put this reference, you don't have to adjust this at all, okay? But it also, I wanted to highlight that you can put this reference anywhere. I could have the reference up against the ceiling if I wanted to, as long as the tracking camera can see both the object and the reference board. So now I'm going to go up here to this portion where I'm going to do this setup reference. And so now I am looking through the tracking camera of the software. And so now we've got a couple different viewpoints. So this is my webcam view here, and then the tracking camera is over to the right. And so it's a little bit confusing, but essentially I'm going to tell the software to find this reference. So I'm going to hit this set reference button. And so now the tracking camera of the sound brush is looking for that checkerboard pattern. It knows how big the square is supposed to be, and it knows what the pattern should look like. And so you see it knows where the camera is with respect to this reference board. And so now the camera's position in 3D space in my room here is known, and it knows exactly where the test object is with respect to the tracking camera. Okay. So it finds these angles and distances and everything. So now my tracking camera and object under test are determined. So now I'm done with this board here. I don't want to move the object or the tracking camera from this point on, right? Because now those are sort of in 3D space. So next I want to pick my sphere color. And so I'm going to pick up the sound brush, and I'm going to use one of these buttons down here. I'm going to hit that Cal button. And now you'll see that the sphere is going to light up, and the software is going to ask me to put this lit sphere in that red icon there. I hit Cal, it cycles through a couple different colors, and I get that crosshair. And that crosshair means the software knows what color the sphere is going to be, and the size and XY position is changing in real time. Okay, so that gives me a warm fuzzy that I've got the position of the sphere tracked very well. Last thing to do is zero out those gyroscopes. So this stand, the precise angle, of that stand is known, and essentially the software uses that to zero out those gyroscopes. So now it kicks me over to the acquisition page, and it knows exactly the position and orientation of that sound brush. And so now what I'm going to do, I'm going to turn on my noise machine here. And I don't know if you guys can hear that or not, but essentially I'm going to hit this preview button. And now you see a live model of the sound brush in the software, as well as the intensity vector sort of measured at the end. But this just highlights how in real time it can calibrate for the position and orientation of the sound wave. Okay. Using that tracking position or tracking platform and then inertial platform. So now I'm going to take some data. I'm going to get this stand out of the way, and I'm going to take some data, and we'll see how the rest of this test works. But watch, I don't have to restrict my motion. I just wave it around however I want. And you see how it stopped taking data there when I moved too far outside of the test area. I was not looking at my LEDs. I was watching the screen there, but oops, and I accidentally initiated a second measurement. So actually this will help me highlight a little bit of another feature. So now I'm going to go and I'm going to change back to just the software, since we don't need to see the live webcam anymore. And so I've got this measurement. This is obviously when I was talking, and so you get some kind of junk measurement, right? Not to be concerned, it automatically stored both of my measurements. So you see I have two measurements here. I can just turn that one off. I don't need it. It was an error, but I can select this one. And now you see I've got all those vectors that I selected in 3D space, hovering around my object. I've got a couple other displays here. This is level versus time or position. And so you see the levels going up and down as I wave closer to and further away from the object. We also have the frequency information of every individual vector. So this, I'll show you how this updates for each vector location. And then this is a contour plot, which I'll show you in just a minute. So if I look here just on this 3D, I can change the size of the vectors, get a little bit better visibility on my object. And this is a pretty fast and quick and dirty test here, but you see, yep, my noisemaker does emanate noise, and it is sort of broadband in its frequency content. And if I needed to understand how the sound was flowing out, I can get that idea from rotating my 3D model. I can also come in here, if I right click, I can go this point by point method. And so now you see I've got a crosshair in my level versus position. And as I move that around, I don't know if you can see, but there's an individual vector that's highlighted here. And so this is the instantaneous frequency spectrum and instantaneous level versus position for that vector. As I move, you see my sweep pattern. Let's see if I can get to one of these a little bit more interesting red guys here. Okay, so that's this vector position right here, and I see this frequency information is a little bit different. Okay, so it's white noise or some broadband noise, but you see the frequency content is changing as I move around. And obviously the level is as well, because I'm getting further away from the object. Okay, so that's the point by point assessment. And then I can also add things like a cutting plane. And so you see this cutting plane show up here. And this allows me to sort of slice through this 3D sound intensity field with a 2D plane. And you can see I can change the thickness of that plane. And I can also change which axis it's looking around, or sort of which direction. And so if I put it in the Z here, so I'll cut along the blue axis here, and you see I get a 2D representation of the vectors that are inside this field right now. So if I make that thinner, I can kind of slice by slice through a three-dimensional MRI, if you want to think of it that way. And I can see where the sound emanates from my object in a 2D manner. And since I now have a 2D representation of sound intensity, I can also come in here and calculate sound power. Okay, so this is now going to be the area over which I'm computing my sound power, and I get a 55.1 dBA of watts of sound power. And so I could move this around to different areas and see how that compares. I could maybe test a different variant of this same machine, leave this area fixed and place my object in the same position, take another measurement, and then do an A/B comparison, this model versus the predecessor or something like that. Sound source localization, sound power, as well as getting a comprehensive idea of how the sound is emanating around my object, how it propagates away, that sort of thing. So that's a crash course through the SoundBrush software. One of the other things I can do is I can control, the frequency range over which I'm showing these results. So right now, this is intensity averaged between 100 hertz and 4 kilohertz. So the whole frequency band is shown here. However, if I just have high frequency concerns, maybe I don't need to look down at this 100 hertz area. I'm going to go maybe say from 2500 hertz to 4 kilohertz. And you notice the magnitude and vector orientation changes for all of my measurement points. All the same data points are here. I'm just restricting the magnitude and direction of that vector to a much smaller frequency band. And it auto scaled. So if you notice red is 58 here, if I go down and I include, let's see, these peaks are about at below 1000 hertz. So now red is 81, and so I can fix that and leave it manual. And so now if I want to go up and do some comparison and say, 2500 to 4 kilohertz, I should have a bunch of cool blue, right? Because the sound intensity magnitude is way lower down in this frequency range. My vectors all update in terms of magnitude and direction on a frequency by frequency basis. So I'm able to sort of parse those different sources out if their different components are emanating different frequency content. That is a crash software demo of the SoundBrush.